exactly. Okay, cool. Any more questions about equivalence relations? Yeah.
What's below the n?
Here?
Yeah.
Greater than or equal to 1. I just wanted to be clear that, at least in this case, natural numbers start at 1.
And then otherwise greater than or equal to 1.
Greater than or equal to 1 as well, yes. Yeah.
Would you mind doing an equivalence relation for a pair or for like a different pair, like 35 or something?
Oh, the equivalence class you mean?
Yeah, equivalence.
Okay, yeah, sure. So let's say we wanted to compute what the equivalence class of 3, 5 is. And, yeah, okay. So this is going to be things, tuples a comma b, such that 3 comma 5 relates to a comma b. Equivalently, these are tuples a comma b such that 3 times b is equal to 5 times a. This is pretty much the most succinct description you're going to get. But really, if you take my fractions interpretation and realize that this equivalence class is really just all the fractions that are equal to, this is saying, when is one fraction equal to 1 over 1? It's when a over whenever the thing on the top, numerator and denominator, are equal to each other. And then the equivalence class of 3 comma 5, this is all a and b such that this happens. Yeah.
Does the equivalence class have anything to do with being symmetric and transitive, like with any of those quantities?
Say it again?
Does the equivalence class have anything to do with like the reflexive transitive and symmetric?
Yes. So you can only define equivalence classes
Oh, okay.
on equivalence relations. And so to be an equivalence relation, you need to have those properties.
Oh, okay.
Yes. Yeah.
So is this anti-symmetric or?
Is R anti-symmetric?
Yeah.
No. Why do you think? Let me give you an example. 1 over 1 relates to 2 over 2, and 2 over 2 is equal to 1 over 1, or in the non-fraction language.
Oh, right.
Yeah. Make sense?
Yeah.
Okay, I think we're going to move on from equivalence relations. Let's do a loop invariant problem. Okay, so I want you guys to analyze the following code. So it takes as input a real number, or you can think of it as a decimal number, and some natural number some integer greater than 0. So z greater than or equal to. Actually, I'm going to say it's greater than or equal to, greater than or equal to 0. Okay, and the function works as follows. First, it defines a variable power, which equals 1. And then it also defines an index, I, which equals 1. And then it says, while I is less than or equal to n, do the following. Set power equal to x times power, and set I equal to I plus 1.
Excuse me. Can you read bigger and darker? It's hard to see.
Okay.
Can you move the whiteboard up too?
Yeah, like that.
Yeah, just or like.
It's fine?
Chalkboard up.
Yeah, okay. See, the problem is we have to record. Okay, good. Should I sort of rewrite this? Can you see it now? Okay. So we're defining some function. The function takes as input some decimal number and some integer greater than or equal to 0. It begins by setting this variable power equal to 1 and setting this index I also equal to 1. And then it says while I is less than or equal to n, let power equal to x times power, and increment the index by 1. And at the end of the while loop, it returns power. Okay, so what does this code do? Yes, exactly. So this code will, we want it, supposed to compute x to the n, x to the power n. Okay, and now my question to you is to analyze this, find the loop invariant, and prove the correctness of this program. Okay, so does anybody have a loop invariant that they'd like to conjecture? What do you think a good loop invariant is here? I don't know who had their hand up for this.
I is greater than 0. Well, no, yeah, I is greater than or equal to 1 and less than or equal to
Loop invariance. So you're saying I is greater than or equal to 1. And you're also saying I is less than or equal to n, right?
Oh wait,
Is this true?
does that say in the while loop? Does that say I is less than or equal to n?
Yeah, it says I is less than or equal to n.
So that would be n plus 1, right?
Yes. Because remember, you want your loop invariance to be true before the loop starts, each time the loop runs, and immediately after the loop is done. So while the loop is running, we'll have that I is less than or equal to n, but the last time it runs, it's going to bump up I another time, and then it's going to be greater than n. It's going to be equal to n plus 1. Yeah.
So would that not be all one line, like I is less than 1 and I is...
I mean, you could write it as one line. So you're saying just write it like 1. You're saying write it like this?
Yeah, that's fine too, right?
Yeah, it doesn't matter. Okay. Now, these are good loop invariants, and they're important to the correctness of this code, but they're not good enough to show that this actually computes the power. So does anybody have another idea of what a loop invariant would be?
We use like power equals x to the I minus 1.
Yes, good. So he says power is equal to x to the I minus 1. Okay. Now, just intuitively, without giving a proof yet, why do we think this is true? First of all, is it a good loop invariant in that we're going to be able to show that this program terminates correctly? So we have, first of all, we have these kind of bounds on I, and it's easy to see that I is just going up monotonically by 1 each time. So this loop is going to terminate when I is equal to n plus 1. And what is this loop invariants say that power is going to be when I is equal to n plus 1. Immediately after the loop ends, it's going to say that power is equal to x to the n, which is what we want it to say. Yeah.
Would you need to define I before power in the function?
Are you saying here?
Yeah,
It doesn't matter. Why would it matter?
because then when you start, I wouldn't have a value. in
Oh,
power.
okay. This is immediately before the loop starts. So when the loop starts, when you get to this statement, I is defined.
All right.
Yeah. Does that make sense?
Yeah.
Okay. Yeah. Yeah, okay. So you want your loop invariance to be true in the following 3 places. Immediately before the loop starts. Is it true immediately before the loop starts?
Yeah.
Yes, okay. Now you also want it to be true when the loop is running. So this loop runs whenever I is less than or equal to n. So we're also good, knowing that each time it only goes up by 1. But you also want it to be correct in the third place. That's when immediately after the loop ends. So let's look at the last time the loop runs. The last time the loop is going to run is when I is equal to n. I is going to be equal to n. Power is going to do whatever it does, and then I is going to be bumped up by 1. So immediately after the loop ends, what's I going to be?
Oh, great. N.
Yeah, it's going to be n plus 1.
Yeah.
So that's why we're saying as a loop invariant, we have that I is between 1 and n plus 1. Does that make sense? Okay. Good. So this seems like we have enough. If these loop invariants are actually true, then we can prove what we want. And I'm just going to go over how you prove this loop invariant's correctness. Okay. And maybe I'll call this loop invariant star. Okay, proof of star. Okay, we need to verify the base case. And that is before the loop starts. So before the loop starts, we have that I is equal to 1, and we have that power is equal to 1. And for if this loop invariant would be true, we would need that power is equal to x to the I minus 1, which is equal to x to the 0, which is equal to 1. As long as x is not 0. Maybe I should say that. Decimal, not 0. Good. Okay, so it's true in the base case. Now I need to prove that if it's true before this loop, one round of the loop runs, it's true after that round of the loop runs. Okay, so now this is kind of the inductive step, where I show if it is true before a round of the loop runs, it is true after that round. On the test, you won't need to write this. We'll know what you need to do. I'm just writing it just so that you guys know. Okay. Great. Now we just need to do this inductive step. So I'm going to use primes to denote the value of I after this round of the loop has run. And I'm going to use not primes to denote the values of I and power before this round the loop has run. So, by the inductive hypothesis, we have that power is equal to x to the I minus 1 Okay, that's what we're given by the inductive hypothesis. Now I need to show that after all this code in the middle of this loop runs, we still have that the loop invariant is true, but now with I prime and power prime. Okay, so what do we need to do for that? Well, the code says that I prime is equal to I plus 1, right? So after this loop, this round of code is done, we'll have that I prime, the new I, was equal to the old I plus 1. And the code also says that power prime is equal to x times power. Okay, and our ultimate goal is to show this, but with the prime element. So, let me just expand this. I have that power prime is equal to x times power. By the inductive hypothesis, I have that power is equal to x to the I minus 1. So this is going to be equal to x times x to the I minus 1, which is equal to x to the I. Now, I'm almost done. I've figured out what the value of power prime is going to be, but it's not quite how I want it. Right now I have that power prime is equal to x to the I, but that I is the old I, and I want it in terms of the new I. So, in terms of the new I know that this is equal to x to the I prime minus 1, because I prime is equal to I plus 1. And thus I've shown that this loop invariant is true. Any questions? Yeah.
How can you like gauge whether your invariant is sufficient when you find it like? You know,
Okay, so you're saying, okay, we got these two invariants. Is this sufficient? Oh, so what I would say is, usually it's not going to be too complicated. So just look at your statements and say, okay, when, in this case, we know what the end value of I is going to be. We're going to know that I is equal to n plus 1 at the end. You should be able to prove, knowing the terminating conditions of the program, that the program is correct. So in this case, we knew that the terminating conditions of the program is I equals n plus 1. So we should know our loop invariant should be strong enough such that if we just plug in that terminating information, we get that the program is correct. In this case, okay, we knew this. We'll have our terminating condition that I equals n plus 1. Does this tell us anything about power? It doesn't. So we look some more. And then we find this loop invariant, and we say, let's plug in the terminating condition, I equals n plus 1, and then we get power is equal to x to the n. And that's good, because that's our program correctness. That make sense?
Yeah.
You have a question?
Yeah, why for the inductive hypothesis do we have it as power is equal to x to the I minus 2?
Oh, I'm sorry, this is supposed to be 1.
Okay.
My bad.
So once x to the power of I prime minus 1, that's that part over there. We do that after x to the power of I to show that it's the new I.
Yeah, because our goal is to show, assuming that this is true with the old values, it'll be true with the new values. So I mean, we're trying to get this equality in terms of the new values, and so now I trade this old I for the new I.
So wouldn't that be I prime plus 1?
No, it's because I prime is equal to I plus 1. So I is equal to I prime minus 1. So now when we trade this I, we know that I is equal to I prime minus 1.
Oh, I see.
Make sense? I think you have your hand up, right?
Oh, nah.
Okay.
So why does that statement just prove everything?
Why
I
does
get it.
this statement just prove everything?
No, like.
Oh, this statement?
Yeah,
Yeah, okay, so the idea is we want to show that this statement is true before the loop starts, every time the loop, and every time after a round of the loop ends.
Oh, so we're just basically trying to get to
that?
Yeah, exactly.
Just like induction?
Yeah, exactly. This is induction. Does that answer your question?
Yeah.
Yeah.
So I saw some examples like online that were a little bit trickier where they had basically like 2 of those statements that sort of had to be proven. So is there going to be anything that like tricky on the test?
So I can't-
Mostly going to be like one.
I would say that what you're going to see on the exam is consistent with what you've seen on the homework and the presentations.
Yeah, there was a quiz that had to do.
Did somebody else have their hand up? Yeah.
Yeah, I was just gonna ask, like, do you think we'll have like binary search and solution sort and like analyze the loop invariance eventually?
So I can't speak to the actual problems on the test. So,
No, that's fine, but like, do you think that we should practice?
do I think you should practice insertion sort and stuff? I don't know, did he talk about that?
I mean, so the problems are not going to be time consuming and hard enough, but if you really want to practice in a way that you think that it's going to aid you in the exam, why not? Right? But we can't speak
No,
specifically as to what
understand.
problems.
I was just like asking, like, do you think like it's a good idea? That's fine.
The point is that if you know how to do loop invariance, it wouldn't matter if you know, it wouldn't matter the type of problems that you're going to see in the exam.
Are we also gonna have to prove the minor loop invariance, like the first one, the first 2 loops? Or first one, I guess it's just one.
I mean, I don't know, but if you do have to prove it, it's.
I know, it's easy. So that one's just, this is for program records.
Yeah.
I wasn't sure, but I think the professor said that we were supposed to get our quiz 6 back today.
Yeah, you will.
Okay.
Or you hopefully will. There's one more round. Yeah?
And we also have to prove termination, right?
Yeah, so you'll need to say, like, prove when this loop terminates, and then plug in your terminating condition to your loop invariance to show that. But this is kind of like the hardest part, so I just have to do this. Okay, good. I think we need to move on from loop invariance, and now Giannis will take over.
Yeah, it's okay. Just the right up corner is not of your problem.
Is Ying coming with the other exam?
She didn't. I texted her.
I will start with designing an NFA and transforming it with an equivalent DFA. It's kind of so it's definitely that you're gonna see that. If not in the final, you're gonna see that in any other course that will follow up this thing. So you need to know the process. Designing the NFA is pretty much straightforward. It's easy, it's simple, you need to do this properly, and it follows the way that you think. Designing the equivalent DFA just without designing any other NFA is not easy. So you need to know the process for the transformation of the NFA to the DFA. You need to do this in the right order, so you don't do anything wrong, and you will have the correct result. If you don't follow the steps properly, you might miss things out. So we want to design a machine that recognizes this line. AD start, 4, ABA star. Okay? Now, we said that the NFA follows the way that you would think. So we want a machine that will recognize this kind of language. This consists of two different expressions. The NFA will be able to decide what kind of expression it will see in front of it, and it will judge which path it should follow. In fact, what it will do, it's not that it's smart, but it's really hardworking. It will take both of the paths, and if one of them accepts, it will accept the general. If it doesn't, none of them, then it will reject. So you need one machine to recognize this language, and another to recognize this one. Okay? So you will start at an initial state, and then you will follow two different pathways. The machine will decide which pathway it should follow each time. So the first pathway should recognize this part of the expression, AB star. And the other one should recognize ABA star. Clear? How will the machine make the decision? Yeah.
As long as you're both arrows.
So the machine will decide by itself, and independently it will choose either this pathway or this pathway. And we said, in fact, it will take both pathways. Yes?
What does the epsilon represent?
Okay. This is a bad question for today. But anyway. The machines recognize a string. Right? You have a tape that has written all these symbols on it in a row. And reading its symbol, let's say that you start at state Q0 and you read that symbol, the input that we have. Okay? If it reads the first symbol, it will transition to another state, let's say Q1, and it will read the rest of your input. As you see, I discard this symbol, I have the transition to a new state, and I need to read the rest of it. The epsilon transitions mean that I can have a transition from Q0 to another state, Q2, without reading any symbol. So my input string is exactly the same. I have a transition that depends on no input symbol. This is the epsilon transition. The machine has a transition to another state without using any input character. Are we all clear with that? So, using two of these epsilon transitions, the machine will decide which of those two expressions it has in front of it to recognize. We will construct a machine over here for recognizing A, B star. Okay? Any ideas?
It comes to Q sub 1, so state 1, and state 1 can only go to state Q2 if there's an A input value. And then from there you can do
Something like that. Okay? And then with the B, we do what?
You can, if there's a B, you can just point it back to itself. Well, actually, no. you
Here?
have to- Wait. No, you have to, it's A and B repeating, you have to go to Q3, that's B. And then from there, you can make Q3 repeating to Q1. Or Q2, okay, Q2, yeah, Q2.
Q2.
Yeah, if there's an A input.
And then what?
Q3 final.
Q3 is the final state?
Yes.
And Q1's the final state.
I see an A. Should I accept it or not?
No.
No. So my first state, Q2, will not be an acceptance state. If I see nothing, should I accept it or not?
Yes.
I should accept it. So my initial state that recognizes this part of the expression should be an acceptance state. The empty string should be accepted. An A should not be accepted. A single A should not be accepted. So my next state, Q2, should not be a final state. If I get a B, I should accept the string that I have. But I already have drawn an acceptance state. So with a B, I will get back to my acceptance state. If I get another A, should I accept it or not? I would have AB that I read and I accepted it, and another A. I should do what? Accept or reject? Reject. It's A, B, A. From that part of the expression, I should reject. I need repetitions of A, B, A, B, A, B, A, B. So if I don't end up with a B as my last symbol, I should reject. So this thing is rejected. I get back to my initial search. I have an A, so I get back to Q2. If I have another B, I need to accept this string. It's one repetition of AB and another. So I should accept this thing. And I get back to Q1. I don't need anything more to accept this part of the expression. Are we clear? Now, second part of the expression. A, B, A, yeah.
From Q2, you don't have you don't have to denote like what happens if you get another B. So if it's A, B, B.
Do I?
I mean, it would just not be accepted. So it wouldn't. So just say Q2.
It could do whatever it wants. If you don't, so this is an NFA. And in fact, it's an NFA epsilon because you have the epsilon transitions. Right? In an NFA, there's no need to define for every state what happens with any input symbol that you could get from your alphabet. Right? So since I don't state anything here for what happens when I have a B at this point.
Oh wait, okay. So I meant from Q1, I guess then. So like if you go from Q1A to Q2.